All right, let me drop my camera down so you can see me. Okay, thanks for inviting me today, David, and good morning to everybody in the US and good afternoon to everybody in Europe. So my talk today is fairly high level. I'm working on on a project with the Energy Systems Integration Group right now, looking at improving the weather and climate inputs to electric system modeling. It's something that I've had a passion for about a decade now. I'm going to look at the current status and what needs to change. And I know everybody in this group is really interested in this topic. So I want to sort of give the US view of what ESIG is doing and where we're at, and give you perhaps a few reality checks of where we actually are deep in the industry as well. So got a little quote here to start with that I've always liked, which is, your assumptions are your windows on the world. Scrub them off every once in a while or the light won't come in. It's from Alan Alda, famous from MASH. Played Hawkeye, and I always thought that was a great quote. So a little bit about me really quickly. I won't belabor this. Basically, I've been in the energy business since 2004, sorry. I'm a meteorologist by training. Used to be a software engineer at the very beginning of my career, from 91 to 95, and then I moved over into meteorology, and I did my PhD on the dynamics of wind in the Columbia River Gorge with Dr. Cliff Mass. And the Columbia Gorge now is an area that has about 5 to 6 gigawatts of wind energy located in it. Did 6.5 years at Iberdrola as the Director of Operational Meteorology within Asset Management, and I've been an independent consultant now for 10 years. So I think everybody in this group is well aware that we have an increasingly weather-dependent system. Previously, the system used to be moderated by temperature mainly, along with relative humidity and solar insolation, basically moderating load. And now we're moving rapidly over to a system which is defined by weather conditions, in that they basically define whether or not there is generation from wind and solar. So previously, if the temperature went up, the load was moderated, and now if the wind stops blowing, we stop having wind generation in the areas where it stopped blowing, and if the sun stops shining, that's also true for solar. So rather than spend much time on there, I'll go straight onto the next slide, which is actually a little bit of a complicated slide showing how all of these things interact within the energy system. And what I've tried to do here is give people an idea, both on the from the atmospheric sciences side and from the power systems side, of just how interlinked the Earth system now is with the electric system. So each of these lines is basically a linkage. The thicker the line, the more powerful the linkage is. They're not to scale, but I tried to do my best job. With hydro, that linkage is very variable according to river management. And the red lines are indications where there's a linkage, and that linkage can be massively amplified by certain weather conditions. So for instance, if we have extreme cold or extreme heat, the linkage to thermal generation suddenly becomes really important. If we have an event where we have icing, then where we have cold temperatures, then the link to humidity becomes very large for wind generation because of icing on the blades, etc. So I've tried to show all of those different types of linkages as well as I possibly could. And as you can see, it's a very complex system, and there's a lot more than is just shown here. There are other linkages which I haven't even considered. These are just the primary ones. So in order to be able to model our electric system, use it for the purposes of doing capacity expansions and production cost models and similar types of modeling, we need to be able to represent the weather as inputs to those power system models. And so we need to do that at spatial scales that are relevant to the system being modeled. They need to accurately capture the resource drivers and their variability. need to capture the uncertainty in forecasts of the resource drivers, so that, for instance, if you're doing production cost modeling, you can you're able to have an idea of the uncertainty in your unit commitment, and you need to do the same for drivers of system load. They need to be physically consistent and concurrent, and this is something that the power systems community often doesn't realize. I think increasingly most people at the kind of research level do understand that, and there has been enough cross-pollination, but I can assure you that from my own experience within the power business, at the operational level, that is not really well understood yet. It's certainly not understood with respect to utilities doing intermediate resource planning. So all the variables need to represent the same time, and they need to be dynamically consistent. So this an example here on the right. I've just tried to show this dynamical consistency idea. These are 3 plots from yesterday, from 0Z yesterday or today, of 10-meter wind speed, which I just took from 3 different models. And you can see, if you look at, in the general pattern, they all look the same, but they're all different resolution and they're all from a different model. And if you start looking at the details, you can see that the wind field is actually significantly different in some places. So if you were to, similarly the temperature field. So if you were to take temperature, for instance, from one model and wind from another model, they wouldn't be dynamically consistent. You wouldn't be representing the same scenario in your model. So an example of where we do that regularly at the moment is we use NSRDB at the same time as we use the Wind Toolkit in the US. That's not an egregious example, but there are considerably more egregious examples of where we're dynamically inconsistent and people don't realize it. And then we also need to provide a representative time interval and a temporally consistent with biases throughout that time period. So ideally, we would want at least 30 years of data, and we wouldn't want to see the model changing over time, which is another issue. So having model and initial condition and boundary condition consistency, and then I put in parentheses here that we need to have the ability to represent the non-stationary climate system. And I put a question mark on there because I think this is important, but I think there's a lot of emphasis on being able to represent the changing climate in models right now, and in weather data sets. I think somewhat we're putting the cart before the horse because we actually don't have good weather data sets going into the power systems models yet. So in many ways, I would like to see that problem solved first. So the main concurrent components are a renewable resource data set, which is truth for wind and solar, a renewable resource forecast data set, which basically provides you with the forecast into the future for each of your time steps of your truth data set, and then a load and load forecast data set. And this particular slide I would provide a lot more detail on if I was talking to an audience that was less well versed in this than you guys are, but I know that everybody on this discussion knows a lot of this already. So I wanted to sort of talk about what's being used in the US right now. Most of the studies that have been done by labs and things are using the National Solar Radiation Database and the Wind Integration National Database, which is the NSRDB and the Wind TK sets. The NSRDB is at 4 kilometers with a 30-minute interval. And Wind Toolkit is at 2 kilometers with 5-minute output. And then the forecasts are at 6 kilometers. The Wind Toolkit is rapidly becoming archaic. It uses an old version of the WRF. It represents a period from 2007 to 2013. And it really needs to be updated. NSRDB is a great data set in that it has high resolution, observationally based solar data in it, But the other variables that are in there for temperature, etc., are actually from MIRA-2, which is at about 60-kilometer resolution and has been downscaled to 4-kilometer. The reason I bring this up is that to a lot of atmospheric scientists, it's like a no-brainer that you probably shouldn't be using that temperature data at 4 kilometers and expecting it to represent what's actually going on. But what happens is when folks are provided with this data, they don't realize that there's that issue because they're not atmospheric scientists. It's not that they're intentionally doing something wrong, they just don't realize. So other data that is being, those are the gold standard. Other data that's being used is MIRA-2 and ERA-5 data, which is not of sufficient resolution to resolve topographic winds. And I'll show you an example of that in a moment. And then the HER and the NAM are often used as well to get longer periods. But the problem with those is they're non-stationary models. And I believe that's a fairly significant red flag, but I'm not sure just how much it is relative to the fact that if you're using output from operational models, at least we've got a long time series. But what you're basically seeing here is we can't satisfy all of those requirements right now of long time series, dynamically consistent, et cetera, with one data set. Another set of data that's used frequently is observational data. And actually, this is the most used data in power systems modeling right now. It's used by a lot of professional consultancies, and I'm going to talk a little bit about that. And I've uncovered some pretty shockingly bad methodologies. And I wanted to make sure folks here understood just how bad things actually are in the real world. So a little bit about resolution and reanalysis data sets. I'm not sure if this animation is coming through. David, can you give me an indication of whether you guys can see the animation?
It's animating, it's fairly jerky.
It's fairly jerky. Okay, so what this is actually an animation of is, and I'll see if I can get my pointer here. Here we go. So I've got my laser pointer on. This is actually Mount Hood in the Cascade Mountains. And this area here where you see the low area is the Columbia River. This is the Columbia River Gorge, which is what my dissertation was based on. And this is a high resolution model run at 1 kilometers at a time when I was actually doing research still, or at least a little bit of research. And what you're seeing here is the wind field over time, 20 minutes apart. And you can see that there's a wake behind Mount Hood here, and you can see all these mountain waves coming off the mountain. And these areas here are wind farms that were owned by Iberdrola, or are still owned by Iberdrola. And what you can see is that you really have to have that high resolution view to be able to understand what's going on at these wind farms. This is about almost a gigawatt of capacity between these wind farms. And the blue dots here are actually the MIRA resolution. So you can see that you clearly aren't able to resolve the wind field within MIRA.
Justin, just say I don't think people can see your pointer. Sorry, I couldn't either. I was sort of battling on anyway. But can you sort of point out where Mount Hood is and sort of describe it, perhaps?
Yes, I'll see if I can do it with the highlighter. Oh, doesn't look like I can. Maybe if I switch to the other screen here. All right.
Oh, yeah, that works.
That's better. Okay.
Yeah.
So Mount Hood is right. Mount Hood is right here. Here's the wake from Mount Hood. These are the mountain waves, and the wind farms are right here and here and here. And there are a bunch of additional wind farms off to the east here. What I've done now is I've gone from MIRA resolution to approximately ERA-5 resolution. And you can see that even at that higher resolution with the ERA-5, we're not able to resolve what's actually going on at the wind farm. So we're going to have to use some other methodologies to be able to get the actual variability if we want to understand that for power systems modeling. And there are techniques that are developing for that, as you guys know, and that's one of the areas I want to talk about to get more discussion from this group, because that's not an area that I have much expertise in. So I wanted to do a fun example of data misuse. So This lady who works for a utility has come along to their consultants. They're doing an intermediate resource plan, and she says, here's our load and wind and solar data for the study. And the consultant says, that's great, but I don't have, it's not coincident and it's not long enough. What should I do? And so the utility employee says, I don't know. So he says, okay, well, I'll have one of my sharp engineers work something out. So he goes over to Ted and he says, can you clean up and fill this data? You know that the PUC wants 30 years now. And so Ted says, let me think about it. I hate that wind toolkit data. Seems to have a really high bias. And this is something that I hear in the industry all the time. But since we've got the actual wind data, I'll work with that instead of using the wind toolkit, and we'll synthesize the load from the temperatures like we usually do. So he's got his solar project shapes from NSRDB. He's got wind project shapes from the facility. He's also got some wind project shapes from the wind toolkit. He's got average RTO temperatures, and he's got a database of utility loads. And you can see all the times are different on these. So he's trying to make a full data set from 1991 through to 2020. So what he says is, I've got it. We've got 30 years of temperature. So what I'm going to do is I'm going to find the nearest temperature match around the same time of year. So he's taking a 5-year window and he's looking either side for all of his years of temperature data, and he finds the best match. And he says, well, it matches in temperature. So that means that it'll be a similar day, right? So I'll just use the same wind and solar shape from that match. So you notice that I've changed the title here to being a fun example or a reality check. Well, this is actually how it is frequently done in the US today. And anybody who's an atmospheric scientist is probably shaking their head right now. The consultant says, will it work? And the answer, the refrain I've often heard is, should be close enough, it's just weather. And we do similar stuff for load. And the client's pleased because they get a long data set, and the PUC doesn't say anything about it because they don't know any better. So Ted gets to work on his modeling and he produces his study results. And now you've got a resource adequacy study result and a capacity expansion study result that are based on data that is essentially not appropriate for the use. And the client's happy, and Justin wants to put a bullet in his head. So that's kind of basically where we are in the sort of state of the industry right now. So I think that we need to educate, and we need to cross-pollinate, and we need to validate. We've really got to work together and understand this problem space. We've got to validate everything, not just the averages, the distributions, but also the distributions, but also the tails, and I'll show you why, an example of why in a second on that. And we need to make sure that the distribution are coincident tails, and what I mean by that is the tails of temperature, wind, and solar, where we're resulting in extreme net loads, must be close to reality. Otherwise, the data value is dramatically diminished. So an example from the wind toolkit that I actually just recently found in a study that I did for a client was, which shouldn't have been a surprise to me, but the light bulb suddenly went off for me when I was doing this study. I've worked in the Northwest for a long time, and I realized that the data in the Bonneville Power Area, which is the balancing authority for the Northwest, has always been notoriously difficult to forecast for wind power because of this issue that the models do a really poor job with the stable boundary layer in the wintertime, which was the focus of the WFIT2 study, and also the very complex terrain needs a minimum of 1.33 kilometer resolution to be able to resolve it, as we saw in that animation a little earlier. And so what happens is that when you get strong inversions, you get weather systems moving across the region that don't remove the inversion, but the model mixes it out. And so you end up with a situation where your model data is implying that there's generation in the 23 to 25% capacity factor range, while meantime, the actual generation from that area is 3%. Now, if you think about putting that data into a resource adequacy model, you're not going to get the right result, and it's a tail event, so it matters. So I wanted to really make that clear, why we need to validate, not just validate against averages. So we've set up this task force, which has basically the following 4 objectives: to establish best practices for introducing historical weather into resource adequacy analysis simulations in the face of data limitations. We understand we're not going to have the perfect data set, so we need to teach people how to use it the best way possible. Develop concrete and detailed descriptions of what's needed from a national power systems weather database and hopefully an international power systems weather database, and translate that into a compelling request to fund it. Now, I personally think this is low-hanging fruit. We're spending trillions of dollars on the energy transition, and yet we can't spend a few million to actually understand the resource. And meanwhile, I read a report just when I woke up this morning. Elon Musk has told the Spanish that Spain could power the entire of Europe. Just build one big solar plant, Spain can power the whole of Europe. Well, if you've listened to this talk, hopefully you realize that that is a ridiculous statement. But the Spanish authorities have engaged with him and said they're always interested in talking to investors. Anyway, provide recommendations on how to plan for high impact, low probability events in power system planning. Do we need to change our reliability criteria? We usually look for 1 day in 10. That's probably not sufficient. And then determine to what extent the power systems modeling should endogenously simulate weather-driven impacts, or whether it should be whether it's external. I've kind of talked about the stakeholders already: the power system modelers, utilities, public utility commissions, and decision and policy makers, and then energy system meteorologists. And I view the energy system meteorologists as the glue that allows people to understand what the limitations of the data are. We've talked about the current practices already. They're archaic and simplistic and often, frankly, flat out unscientific.
Justin, do you have many more slides left?
No, I've got one more, I think. Okay, I'll go to the next one. So our initial focus is basically in defining the requirements for this ideal data set. And our promising starting points are the wind toolkit. I was talking to Carolina Draxel at NREL yesterday. They're doing some pretty major extensions to that, and the NSRDB is also improved with GOES-R. And then there's a project to do that is basically producing a CONUS-wide data set at 4 kilometers for 40 years. So that's sort of kind of an appeal to this group to realize just the magnitude of the problem. And I've put a link to a Google document in here that I hope that everybody will consider putting their thoughts in. Thanks.